Okay. All right, let's do this. Now, this lesson is something I basically did, but I'm going to add some things to it. But I'm doing this filming so that you can more completely understand. Thank you, Miguel. I appreciate your help. Yeah, thank you for poking him. I know he wasn't listening. He didn't see me. He's looking at me, but he sees something horrid in the front of the room. He doesn't recognize it as Mr. Darcy, right? Thank you very much. Nice assist, Alex. So this is going to help you make better sense of this in 48 hours when the understanding starts to fade. You can look at this and refresh things, okay? All right, so the key ingredient here is this relationship. If I take water and I produce H plus, it's really hydronium, it's really this, but it's just easier to write. Molar concentration, brackets, right? Brackets, M, and the hydroxide ion. Now, this breaks down in pure, absolutely pure water has a concentration of -7 and -7. Absolutely. If I multiply those together, I get a constant, which, what did I just say, Armindo? What word did I just use? The C word? Constants. You get a constant value if I multiply these together of 1 times 10 to the -14. 1 times 1 is 1. 10 to the -7, 10 to the -7 is 10 to the -14. Are you okay with that? Okay, good. Now, what I want to do is, I want to put in here the salt of a weak acid, okay? A strong acid, the major strong acids that are very common are nitric acid, sulfuric acid. Those are the biggies, right? When you think of strong acids. Yes, there are others, but those are the big ones. Yes? When you're thinking of a weak acid, what's the mother of all weak acids that we're going to use a lot in here? We're going to use something that I haven't told you about yet. But we use in here, because we studied it when we did equation writing, carbonic acid. Remember, carbonic acid, when you produce a weak acid, it breaks down to carbon dioxide and water. So when you take two salts, two acids, and you combine them, a salt and a weak acid, let me explain. If you take this, you ready? If you take sodium carbonate and mix it with sulfuric acid, right? I'm going to put the products down here. You produce sodium sulfate plus carbon dioxide. So if you take the salt of a weak acid plus a strong acid, you're going to produce the salt of a strong acid and a weak acid. Now this is going to break down to the corresponding acid anhydride in water. Remember we did that when we did equation writing? Remember that? So this is going to break down to this. Correct? So the production of this gas will drive this reaction, correct? Because doesn't that gas go out of solution? Doesn't it? It bubbles out. So when you're shifting the equilibrium, remember we spoke about shifting the equilibrium? If I get rid of that gas, I'm getting rid of product, aren't I? Which allows me to make even more product until the reactants are gone. So that drives that reaction, the production of that gas. Clear? Are you okay with that? So we use carbonic acid for two reasons. One, we introduced it when we did equation writing, and it's the way the body disposes of carbon dioxide, there's a relationship between these two ions. There's a relationship between this ion, carbonic acid and the bicarbonate ion, correct? There's a relationship there. Now, if carbonic acid were a strong acid, remember, if you take an acid anhydride, such as carbon dioxide, you mix it with water, you produce what? The carbonic acid, correct? Now, that's how the body gets rid of carbon dioxide. Because carbon dioxide is an acid anhydride, we know that that exists. Acid rain, you produce sulfur dioxide, you produce an acid. If you mix the sulfur dioxide, which is an acid anhydride, with water. So we understand where acids come from relative to ternary acids, acid anhydrides, and water. We know that relationship from equation writing, correct? So we use carbonic acid to start off with because if it were a strong acid, our body would be digested by just that acid. So it's got to be a weak acid, right? Okay. So I'm going to take, and I'm going to put in this reaction, I'm going to take and I'm going to dump in 1 mole of sodium, 1 mole of sodium carbonate, a whole mole of sodium carbonate, I'm going to dump into this water. Okay? Is that okay? I'm going to use red. So let me erase the stuff up here. This is my scrap sheet up here. Okay? And let me put up there the equation. It's going to be sodium, which is sodium is the ultimate spectator ion, correct? Not going to do anything. I have the sodium carbonate, and I'm going to produce 2 sodium ions plus carbonate ion. Is that okay? Yes or no? So if I take 1 mole of this, I'm going to get 1 mole of this. So for every mole of sodium carbonate, I produce a mole of carbonate. Is that okay? Yes or no? Yes? Okay, good. Now, we're not going to use the dissociation constants or anything like that yet, and you'll know what I mean by that the next class. Okay. So the question is, what will this carbonate do? What will it do to the pH of this water? What will it do to the level of the hydronium ion? What will it do? Will it increase the hydronium ion? Will it increase this? Will it decrease this? Or will it have no effect? And what is it that I'm doing? Okay. So do you understand, if I take 1 mole of sodium carbonate, I produce a whole mole of carbonate. You okay with that? Okay, good. So I take the carbonate, sorry, here's my water, okay, and I produce this. Now, why do I produce that? Remember, if that is a weak acid, doesn't it have a high attraction for hydrogen? Yes or no? Yes. Everybody's shaking their head. That's right. My nonverbal class, they shake their head a lot. Okay? Right? Yes or no? Yeah. Salama's like, cool, do it. It looks like she's listening to some cool music, man. She's like, okay, I got the beat, man. Okay, so if carbonic acid is a weak acid, It likes being that weak acid, correct? So it likes the hydrogen. So if you have carbonate without the hydrogen, what's it going to do? It's going to take hydrogen from there, isn't it? Right? Remember I said that water has this natural quantity of hydrogen ions in solution. Remember I said that? Remember? So it's going to get it really from here, isn't it? Right? It's going to get it from here, correct? Yes or no? And I'm going to produce the carbonic acid. But is it going to get it all from there? I have a whole mole of it. No, it's going to get a lot of it from where? It's going to get some of it from where? It's got to make some new ones, right? Correct? So it's going to take what's there and make some new stuff, correct? Yes or no? So aren't you going to be manufacturing this? Doesn't this all of a sudden get left over? Doesn't it? Yes or no? Yeah, it does. So that's left over. Let's make sure that's on. Okay, so that gets left over. All right? But what has to stay constant? What has to stay constant? Tell me. Come on, Eamon, you can do this, big guy. You can do this. What has to stay constant? What product? What number? Give it to me, big guy. Give it to me. Say it. He's pointing. He has his hand over his face, and he's pointing. He's pointing at the board. You want to be more specific than points? Can I help you? Hot, cold, up, down. What has to be constant? That has to, no, these don't have to be constant. What has to be constant? The product of those numbers have to be constant. That has to be constant. Can that number go down? Can that number go down? Yes or no? Yes or no? Yes or no?
No.
Yes, of course it can go down. Come on, guys. Of course it can go down. Of course it can go down. Yes or no?
Yes.
Yes, of course it can go down. Look, let me do this. Let me do this. I'll do this in black. Are you ready? Let me do this. If I have 10 times 10 equals 100, and I need the left side can be whatever it is, but the right side has to be 100. Has to be 100. Has to be. The left side can be whatever you want it to be, but the right side has to be 1, 0, 0. Is that okay? Okay. So I'm going to make that 10 a 1. What do I have to make the other number? I have A and B. I have two factors on the left. If this has to be 100 and A is going to be 1, what must B have to be? 100, yeah. Do these have to remain the same, Eamon? No, they don't. What's the key? They have to equal that. These don't have to be equal, but they have to equal this. You get that? I'm so glad you didn't understand that. Do you get it now? That's really big. Are you sure you understand that? That is, you have one of the keys of the kingdom of chemistry in your pocket. Take it. Take it. Put it in your pocket. Thank you. Excellent. And you can, if you're feeling sad today, this is what you do if you're feeling sad. You go like this. Excellent. So, is this number going to go down or up? If I'm stealing this value, if I'm stealing that, making more to produce this, is this decreasing? But what's increasing in order to keep that product the same? What must be increasing? The other one. What do we call that other one? You say it, hydroxide. Say the word hydroxide. Say it again. Say it again. I want this camera to hear you. All right, let's not go crazy. Okay, good. All right, it's hydroxide, right? So that number is going to go up, isn't it? So is this number going to be higher than this number?
Yes.
Yes, it is. Does that make it basic or does that make it acidic? Makes it basic. So that's why the salts of a weak acid will make a solution basic. If I say to you, and you don't know chemistry, and I say to you, the salt of a weak acid, if I put that in water, will that make it acidic or basic? What would you naturally say? What's logical? It would make it acidic, right? But it doesn't make it acidic. It makes it basic. And the reason it makes it basic is because it's a weak acid and wants that hydrogen back. Darn it, I want that hydrogen. Give me that hydrogen. I want it now. So it's going to take it. Or it's like, okay, give it what it wants, man. Let's get a little bit less crazy, okay? So it's happy now that it has the hydrogen, okay? Now, let's look at a chemical that makes a solution. It's kind of weird. It also doesn't make sense when you first look at it. All right. Let's look at something else. Okay. Is this ammonia gas? Extremely soluble in water. One of the most soluble gases that we know of. Very soluble. Oxygen. Carbon dioxide. Ammonia. How many people have ever cleaned with water that has ammonia gas dissolved in it? Anybody? So, Alex, may I draw the conclusion that you don't clean windows? How many people have ever cleaned windows? Raise your hand. Okay. What does the stuff smell like? Doesn't it smell like ammonia? They have no idea. Okay. Laura, you look like you're a tough kid who's probably had to clean a floor or two in your life, right? Do you know what ammonia is, or? Yeah, she's shaking her head. Yeah, exactly. She knows. She's no, you know, I know. I'm trying to think of a word that doesn't sound terribly offensive. I know, but you have to do chores at home. Do you have a maid? How many people have maids? Raise your hand. I'm not being mean or anything. All right, half the class is raising their hand, and the other half is denying it. Okay, do you have a maid? Yeah. Yes, so you didn't raise your hand. Okay. All right, okay. All right, I want to know. I'm not being mean. I'm just asking you. How many people have house cleaners at home? Raise your hand. And the hands are going up. It's okay. It's all right. Okay, all right. So some of you know what the smell of ammonia is. When you take ammonia, which is very soluble, and you put it in water, it is good to clean with. And the gas comes out when the water dries and you smell ammonia, right? Okay. Does ammonia make water basic, or does it make it acidic? Anybody know? It what? No, ammonia. Ammonia gas does this. When I mix it with water, it makes this, and I'm going to show you why. This is what ammonia looks like. Remember we did molecular modeling? Well, the reason we did molecular modeling was so that we could understand why ammonia makes something basic, believe it or not. Okay? So remember we said that ammonia looked like this. Trigonal pyramidal. In other words, I take my fist is ammonia, and I go like this. Okay? Not quite. I can do this. I can do this. Okay? I get this trigonal plane here, right? Like this. But it's not very much out of the plane, just a little bit. You see that? But it is out of the plane, so it's called trigonal planar. It's not like this. It's more like this, right? You get it? Yes or no? Okay, yes or no? You with me? Do, right? Okay, now. Well, what happens is I get this unpaired pair of electrons, and H plus goes there. Remember I told you you had that relationship of water, equilibrium relationship. Remember that? Do you remember that? Can you see that on the film? Can you see that? The green?
Sort of.
Sort of, okay. Right? I have that, right? So let me make a little red there. Okay. Looks like Mushroom Mall, okay. Okay, you get it? Yes? Yes? So, if I'm taking some of this and I'm putting it here, which way am I shifting? What am I increasing? The amount of what or what? Remember, this has to be 1 times 10 to the negative 14, right? Right? This is 1 times 10 to the 7th. So what am I, if I take some of the hydrogen away, what must I have to do? Make more what? Hydroxide. So what's going to happen is I'm going to produce this. You see that? It's called it's actually called, it's a salt, sort of. It's a base. It's actually a base, sorry. Ammonium hydroxide, but it's in water, right? It actually looks like this, ammonium and hydroxide. So what am I producing? If I'm going to use this, I have to shift the equilibrium to make more, right? Because I'm taking the H plus away. You see that? You see that? Is it make it really basic or just a little bit basic? It doesn't make it really very basic. It doesn't make it very basic. Because remember, this isn't like completely down. Right? The reason it can go on is because it's negative, it's positive, this is negative, and it's kind of like available, right? Its position, right? It's kind of like these are kind of out of the way, because these are also negative, right? Yes, these bonds are negative as well. So what happens is, let's take those out of the way a little bit, and we'll create some space, literally some space, so we can fly in here and take it, right? You get it? If they were like this, it couldn't get at it, right? If they were like this, like a basket, right? So they're out of the way. But they're not down completely. So it's not going to take a zillion of these, but it's going to take enough to make it basic. Do you see that? Yes or no? So ammonia, is ammonia basic? Does it make water basic or acidic? What does it do? It makes it basic. Do you get that? I'm almost done. You got to give me 6 more minutes. All right? All right, so what is ammonium? Ammonium is the result of this reaction, correct? Okay, now. All right, now. Let's keep this, okay? You know what? Let's rewrite that. Let's rewrite that. These are not working. Oh, there you go. That's a good one. Right? This is 1 times 10 to the negative 7, 1 times 10 to the negative 7, 1 times 10 to the negative 14. You all right with that? Is that okay? Can you see that? Okay, shall I make this darker? Okay, you okay? Now, let's take ammonium chloride. Is chlorine a spectator ion? What's chlorine? Chlorine's from a strong acid, right? Hydrogen chloride, hydrochloric acid. Is chlorine going to be a spectator ion, or is it going to have some influence in the pH of the system? T? Chlorine. Spectator. Okay. So I'm going to take this. Ammonium chloride. Right? So it's going to be ammonium plus chlorine. So what's the I'm going to put that in water. So what's really the operative ion? It's going to be ammonium, right? Yes or no? Yes or no?
Yes.
Okay. I'm going to put dots up here and here. And I'm just going to put those dots in there, okay? And then I'm going to make, what's available now? The ammonia isn't there, is it? It's not there. It's not there. Now remember this. This is important. Can I erase this? You got that, right? Can I erase it? Or should I put it, I'll put it over here. Can you see this? Can you see that box? Yes, okay, good. So, remember this, remember this. Remember this. Remember that? Remember that? Yes? Yes or no? All right. So if I have all of that and I don't have any ammonia, what's going to happen? What's going to happen? Remember, this is equilibrium. For this to exist as NH4, for that to exist as NH4, doesn't it have to have ammonia around somewhere? Doesn't it? Yes or no? Yes or no?
Yes.
Yes. So what's going to happen to this? What's going to happen? What's going to happen in the water? It's a side reaction in the water. Where is it? It's in water. What's the side reaction that's going to happen in the water? What's the side reaction? In the water. Isn't it going to be this? Isn't it? Yes or no?
Yes.
Right, yeah. Isn't it going to produce this? Yes?
Yes.
It's got to, man. It's got to. For this to exist, it has to have ammonia. Sorry. If I put 100% of this in terms of ammonium chloride, soluble salt, remember, all ammonium salts are 100% soluble. It's one of the solubility rules. Remember we did solubility rules last time? That's why I did that. Remember? Group 1 metals. When they're part of salts, they're completely soluble. Sodium chloride, right? Yes? And I also said when you have an ammonium salt, ammonium chloride, ammonium nitrate, 100% soluble. Remember I said that? Remember? Okay, so that's all soluble. So if I put 1 mole of this in, what am I going to get? I'm going to get 1 mole of this. So this is 1 mole, right? Right? It's 1 mole, right? 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 Right?
Yes.
So what am I producing? I'm going to produce what? What am I producing? I'm going to produce what? I'm going to produce ammonia, and I'm going to produce this, which is going to go where? Right? A bond that forms between 2 atoms where one of the atoms is supplying all of the electrons. What kind of bond is that called? Is this hydrogen bringing any bonds here? Any electrons to the bond? Aren't those electrons only from the oxygen? So I'm making what? No. It's called a coordinate bond. Remember a coordinate bond? Look up coordinate bond right now in your book, everybody. Come on, guys. I don't want you to be late for homeroom, but some of you may. I got to finish this. Otherwise, I'm going to be wasting my time. I'm almost done. And who knows what's going on? T. Go down, pack your bags, go see Mrs. Brown. Ask her to email the 10th grade homeroom teachers that you're going to be a little bit late, a few minutes late, okay? Do it right now. You know what? Just leave your stuff and come back, okay? Just do it quickly. What is it called? It's called what? What kind of bond is it? Maybe look up in the index. Do you guys have ever used an index before? Laura, you may want to use an index. Coordinate bond. What do you got? All right, you got to speak clearly. Armindo. A covalent bond in which one atom contributes both electrons to the bond. Is that what it says? Excellent. So this is a coordination bond, right? Right? So when you get this, coordination bond, right? And hydronium. No, I'm not done. So, I'm producing this, or not? In the form of this. Yes or no? Yes or no? I'm producing this, or not? Am I? Yes or no? Am I producing hydronium ion? Am I producing, I'm not going to say hydronium ion, I'm just going to say the H ion for short. Is that okay? So, am I doing this? Water. One times 10 to the negative 7 molar concentration. 1 times 10 to the negative 7 molar concentration. Now, so what am I doing? Aren't I producing more of this? Right? So I'm going to have to consume some of this, right?
Yeah.
So I've got to make more of this. I'm going to have more of this than this, right? So this is going to be high. This is low. Is the solution going to be acidic or is it going to be basic? Acidic. So ammonium salts, do they make water acidic or basic?
Acidic.
We're done. Good? Everybody understands?
Yes.
Excellent.